Welcome to the Deep Dive. Our mission today, well, it's all about survival. We're looking at critical materials. Think about those fan blades in a jet engine. They have to endure just incredible stress, billions of cycles sometimes.
Billions, yeah. It's almost hard to comprehend.
And it's not just the constant vibration, the very high cycle fatigue or VHCF. They also need to survive sudden impacts.
Right, like hitting a bird or some debris on the runway. That's foreign object damage, FOD. It's a huge safety concern.
So the big challenge is making materials tough enough for both the long, slow grind and the sudden shock.
Exactly. And for a while now, a key technique has been laser shock peening. LSP.
Okay.
They essentially blast the surface with these incredibly short, powerful laser pulses. We're talking nanoseconds, but packing maybe 1 to 15 joules.
Wow. And that does what creates a shock wave.
It does, a massive one, up to 10 gigapascals.
Right.
That compresses the surface layer, maybe a few millimeters deep. And that compression really helps boost the fatigue life.
But here's the twist, right? Our sources suggest the old ways of checking if this treatment worked.
Yeah.
They're not quite cutting it anymore.
Yeah, that's the core problem. When you hit a material that hard and fast, the strain rates can be astronomical, like 10 to 10 per second. Things happen differently.
So measuring residual stress, the sort of leftover squeeze in the material, that doesn't tell the whole story.
Not for these shock events, no. It's like trying to understand an explosion by just looking at the smoke afterwards. You miss the actual blast dynamics.
Okay, so the mission became finding something better.
Exactly. Researchers needed a parameter that's, invariant, something fundamental that links that initial shock treatment directly to how long the material will actually last down the road.
And that's where these deeper physics concepts come in. Action invariants and self-similarity.
That's the heart of it. We're going deep into the physics of failure to see how these ideas could revolutionize material design.
All right, let's unpack that. Why exactly does residual stress fail us when we're dealing with LSP?
Well, residual stress works okay for slower quasi-static loading, things below maybe 10 arrows per second strain rate. But an LSP shock wave blows right past the material's normal elastic limit, the Hugoni autoelastic limit, or HEL.
Meaning it's not just squeezing it, it's fundamentally changing it instantly.
Instantly. You get intense plastic deformation, the microstructure rearranges itself in, nanoseconds. It's a mix of ductile flow and brittle cracking happening almost simultaneously. It's complex.
Chaotic even.
Definitely chaotic and non-local. The effects spread. Residual stress is just a static snapshot after all that chaos. It doesn't quantify the intensity of the event itself.
So it measures the bruise but not the energy of the punch that caused it.
That's a great analogy, and that's why they turn to the action invariant, often denoted as $. It's designed to capture that punch. It quantifies the sort of anomalous energy absorption right there on the shockwave front.
Okay.
And that energy absorption is tied directly to how defects, like shear bands, form and organize collectively within the material during the shock.
So the action invariant is basically measuring the energy that gets stored within those newly created defect structures.
In essence, yes. It's a measure of the material state immediately after absorbing that shock energy. It's fundamental to the shock process itself, unlike residual stress, which is more of an after effect.
Got it. So for these really high-pressure shock waves, 1 to 10 gigapascals, you need this action invariant to understand what actually happened.
You do. It's the appropriate physical quantity for that loading regime.
Now, this is where it gets, really interesting for me. The sources link this action invariant to self-similarity. That sounds like fractals, patterns repeating at different scales. How does that apply to metal breaking?
It's a profound connection. Self-similarity here means that certain underlying rules governing how the material deforms and fails seem to hold true across different conditions or scales. Let's start with the shock itself. The shockwave action invariant, which we can call a jaw, is underpinned by something called the Swegle-Grady fourth power law.
Fourth power law.
Yeah. It states that in a steady plastic wave, the rate of plastic strain scales with the stress amplitude raised to a power that's universally close to 4.
Universally close to 4. For different materials, different impact strengths.
Generally, yes. It suggests a fundamental self-similar structure to how that plastic wave front propagates and dissipates energy. It's sometimes called similarity of the second kind.
Okay, and Allah mathematically captures this.
It does. All dollars is defined as the product of the energy dissipated in a small part of the wave and the time it takes to dissipate it. It quantifies that self-similar energy dissipation process.
So that's the shock side. Now, how does this relate to the long, slow death of fatigue failure over billions of cycles? Is there a similar rule?
Amazingly, yes. That's the crucial link. The way fatigue cracks grow also shows self-similarity. This is captured in the well-known Paris law.
The Paris law describes how fast a crack grows under cyclic stress.
Exactly. And the exponent in the Paris law, usually called $, is also often found experimentally to be close to 4.
Wait a second. The exponent is also 4. For both the nanosecond shock wave and the slow fatigue crack growth.
Close to 4, yeah. It's a remarkable coincidence, if you can call it that.
That can't be a coincidence. What does it imply?
It strongly suggests that the underlying physics, the collective behavior of defects, is analogous in both scenarios. Think about the tiny process zone right at the tip of a growing fatigue crack. The way defects organize and dissipate energy there seems to follow similar scaling rules as the defects organizing within the high-speed plastic shock wave front, like those shear bands we mentioned.
So the universe uses the same math rule for breaking things quickly and breaking things slowly.
It seems that way, at least in terms of this energy dissipation scaling. There's a corresponding fatigue action invariant AF ball, which is related to the total time it takes for the crack to propagate to failure, $T.
And that shared exponent of 4 connects A ball from the initial shock treatment to AFA, the ultimate fatigue life.
That's the core idea. It provides a physical bridge between the treatment and the outcome.
Okay, the theory sounds elegant. But how on earth do you measure ALA reliably? You said the laser spot in LSP is tiny and the event is incredibly fast.
Right. Direct measurement during LSP is extremely difficult. The small spot size introduces edge effects and complex wave interactions that muddy the waters. You don't get a clean shockwave profile.
So you can't just point a sensor at it. They needed a different experimental approach.
They did. They needed to generate a measurable, uniform shockwave over a larger area. The solution was to use plane wave loading on relatively massive targets.
Plane wave loading?
Yeah, think of it as hitting the material with a perfectly flat impact, not a focused spot. They use a thick plate, about 15 millimeters of AMG6 aluminum alloy.
And how did they generate the shock? Not with a laser this time.
No, they used impact. They accelerated a thinner 4 millimeter aluminum plate, a flyer plate, up to about 1,400 meters per second.
1,400 meters a second. That's Mach 4 territory.
Yeah.
How did they launch it?
With a specialized explosive setup, actually. A conical lens arrangement to focus the blast and propel the flyer plate very precisely.
So a controlled explosion to simulate the laser shock, but bigger and cleaner.
Exactly. Bigger, flatter, and cleaner. And they used sophisticated laser interferometry, VISAR, to measure the shockwave profile very accurately as it entered the target. Crucially, they did this under recovery conditions, meaning they designed the experiment to prevent interfering waves from the sides or back, giving them pure shock data.
Okay, so that gave them the reliable input needed to calculate the shockwave action invariant.
Precisely.
Then what happened to these shocked aluminum blocks? Did they test their fatigue life?
They did. They carefully machined standard fatigue test specimens directly from these pre-shocked targets.
So the test samples themselves had already undergone that quantified shock treatment.
Correct. Then they put these samples into a VHCF testing rig. We're talking endurance up to maybe 10 cycles, 10 billion.
10 billion cycles. How long does that take?
Well, they use ultrasonic fatigue machines that run incredibly fast, around 20 kilohertz, so much faster than traditional machines, but still a long test.
And were they just waiting for the samples to snap? Or could they see failure coming?
They monitored the internal state using ultrasonic techniques during the test. Specifically, they looked at a parameter called the nonlinearity coefficient, beta relative.
Nonlinearity coefficient. What does that track?
It's sensitive to the buildup of microdamage, like dislocations and microcracks. And they saw something really interesting. Right before the main crack initiated and the sample failed, especially in the lower stress VHCF tests, this beta relative value would suddenly shoot up. An avalanche-like growth.
Like the damage was accumulating quietly, then hit a critical point and cascaded.
Exactly like that. It supports the idea of hitting a critical energy threshold, related to that fatigue action invariant Apiville area, which triggers macroscopic failure.
Okay, so the mechanical test linked the shock invariant ALAR to the fatigue life and this critical failure point. Did they look at the actual broken surfaces?
Yes, that was the next crucial step. They used quantitative factography, basically analyzing the microscopic roughness of the fracture surface.
Why roughness? What does that tell you?
Roughness is related to the energy dissipated during fracture, but it also contains information about the process of fracture. They were looking for scale invariants in the roughness itself.
Scale invariants. That self-similarity idea again.
Precisely. They used a parameter called the Hurst exponent, old dollars. It's a measure derived from fractal geometry that quantifies the jaggedness or smoothness of a surface across different scales.
And what did they find when comparing the shocked samples to the non-shocked ones?
This was quite revealing. The samples that had been pre-shocked showed a noticeable decrease in their Hurst exponent after fatigue failure. It went from around 0.58 or 0.76 for the untreated material down to 0.34, 0.58 for the shocked ones.
Wait, the shocked samples had smoother fracture surfaces? That seems counterintuitive. I'd expect a more damaged material to break more violently, more jaggedly.
It does seem odd at first glance, but think about what the initial shock did. It created a very high density of fine-scale damage, intense dislocation networks throughout the material. It sort of pre-fragmented the microstructure.
Okay.
So when the fatigue crack eventually tries to grow through this pre-fragmented structure, it can't easily follow nice ordered paths along crystallographic planes, which normally creates rougher surfaces. It can't form those typical ordered defect structures like persistent slip bands as easily.
So the initial shock-induced messiness actually prevents the fatigue process from creating its own typical rougher form of organized damage. It forces the failure to be more distributed, maybe?
That's the interpretation. The initial high strain rate damage homogenizes or complicates the subsequent fatigue damage localization. The crack path becomes less correlated, leading to a lower Hurst exponent, a statistically smoother surface.
Right.
It's physical evidence that the shock fundamentally changed the failure mode.
That makes sense. It's a signature of the shock's influence. So, did they manage to translate this understanding into practical benefits for actual aerospace alloys?
They did. The sources mentioned tests on VT6 titanium alloy, which is, very common in aircraft engines.
And they used actual laser shock peening this time.
Yes, using a standard industrial laser setup. But they added a crucial refinement based on this understanding. After the LST treatment, they performed very careful fine grinding and polishing on the surface.
Why polish it? Wouldn't that remove some of the treated layer?
They were careful to only remove the very top surface roughness that the laser process itself can create. Those tiny ridges and valleys can act as stress concentrators, becoming initiation points for fatigue cracks, which masks the real benefit from the shock-induced changes within the material.
So they wanted to isolate the effect of the subsurface compression, and that changed microstructure, not just the surface topography.
Exactly. Preserve the hardened layer, remove the potentially detrimental surface features.
Smart.
Yeah.
And the result? Did it improve the fatigue life?
It did. They reported an increase in operational characteristics, essentially fatigue life, by about 9 to 10% in the VHCF regime.
9 to 10% might not sound huge, but in aerospace, that's significant.
It's very significant, especially in the VHCF regime where failures can be unexpected. And the example they gave was quite dramatic. An untreated VT6 sample tested at 460 MPa failed after about 500 million cycles, $5.47, 180 odd.
Yeah.
A laser-treated and polished sample not only survived much longer, $2.22 times 199 cycles, so over 2 billion.
Wow, almost 4 times longer.
But it did so at a higher stress level, 475 MPa.
That's impressive. Longer life at higher stress. Clear proof the optimized treatment works.
It really demonstrates the potential. The optimized shock input, informed by the action invariant concept, fundamentally boosted the material's resistance. So bringing it all together, the path forward isn't just about applying LSP and hoping for the best based on residual stress. It's about optimization using these deeper physical principles. The goal is to use the two invariants, os from the shock and os related to fatigue, to set up a formal optimization problem.
Like a mathematical equation to find the perfect treatment.
Essentially, yes. It's framed as a minimax problem. You want to find the shock parameters, the pulse amplitude and duration that maximize the subsequent fatigue crack propagation time under the expected service loads.
Maximize the lifetime by choosing the optimal hit.
Exactly. You're leveraging that fundamental link, that self-similarity reflected in the power laws, to design the most effective treatment based on physics, not just empirical correlation.
So we started by looking at how to make aircraft parts last longer, went through shock physics, fractal dimensions, explosive impacts, and landed on this idea that a deep concept from physics, the action invariant, is key. It connects the initial shock treatment to how tiny cracks behave billions of cycles later, potentially better than our old engineering metrics.
It's a fundamental shift. And the really provocative thought here is the universality of it all. The fact that these two incredibly different processes, a nanosecond shock wave and fatigue over years, seem to obey the same underlying fourth power self-similarity law. It hints at something profound about how materials organize themselves on the path to failure.
A universal rule for breaking stuff.
Maybe. This focus on non-local collective defect behavior captured by these invariants is likely essential if we want to design materials for the next generation of truly extreme service life requirements. It's a whole new way to think about fracture mechanics.